The agenda is we have the ISIS for high availability enhancements, which is I'm going to talk about it, which has two methods, checkpointing method and the IETF restart TLV method. And then ISIS for IPv6, which is already there, but I'm going to cover because the following topic, the multi-topology support necessitates that, so that there is a continuity. And then the MD5 authentication support. These topics are actually part of the IETF, and the other topics that include some of the enhancements from a service provider can take advantage to make it more operator efficient in their network for the protocol to run, which includes the default metric, the protocol shutdown mechanism, and the limit the number of redistributed routes. And I'm going to talk on the last topic, some of the topics, which is update on IETF drafts. So I tried, as you see, I'm from Cisco, but I tried to not to have any vendor-specific information. So this particular presentation as such is going to cover what the protocol does, and that's just leave it at that state. And if you need any additional information, you can get it from the respective companies' websites. The scope of the presentation, as I was alluding to, is to present the recent ISIS enhancements. Obviously, some of these enhancements to the IETF, which is a standards organization, and also for the network operator to improve the operating efficiency, which is the last agenda, or the last topics in the agenda. So what is HA, which is high availability, is actually the ability to improve the efficiency in your service provider network, to improve the availability of the networks. So in the context of the routing protocols, it actually, the high availability translates to two things, which is to maintain the traffic forwarding and to maintain the adjacency while there is a component failure here, which I'm referring to anything, whether there is RP failure or whether there is a routing protocol. Basically, in this case, it's a routing RP failure. And when you have a HA, which is comes with the following terminologies in order to understand the subsequent slides, we have a starting router, we have a restarting router, and we have a neighbor router, and then we have a NSF capable router, and NSF aware, and NSF unaware. So the last one, which is the NSF unaware, is a normal router which does not understand any of the extensions of the high availability. So if you do understand, then you become aware. So I'm kind of working from the bottom of the bullets. So when you do understand, then it becomes NSF aware. And if a neighbor understands, the neighbor also becomes NSF aware router too. And a router which is actually experiencing the restart, that means there is a route processor which is, has, crashed, and then you have a redundant RP which is coming, then it becomes a restarting router. And then if you are actually coming for the first time, then it is called a starting router. The terminology, is that clear enough? The NSF in that refers to the non-stop forwarding, which is basically the ability of the router to continue to forward the traffic towards a router which is actually experiencing the restart, and also from the restarting router point of view, to continue to forward on the forwarding plane even when there is a component failure, which is the RP switchover. So what actually happens in the normal mechanism when a router restarts? The neighbor routers, detects that, there is a router which actually restarted and causes the adjacencies with the restarting router, the router which is restarting, through the downstate, because the adjacency is an upstate, so it goes through the downstate. And this event will trigger the LSP generation, and then we get into flooding, and then the SPF computation, and also possible flapping because of the routing table. So this is obviously undesirable from a non-stop forwarding point of view. So the idea here is to localize the restart event to a box rather than a network-wide. So when we talk about high availability in terms of the extensions that are done to the protocol, we want to localize the event to a single box rather than a network-wide event. So I was mentioning on the restarting router, it causes to compute its own routes before achieving the database synchronization. Similarly, the neighbor routers detect the restarting router is restarting. So they're going to regenerate the LSPs, and obviously it's going to set the SRM flags. And on a point-to-point links, they transmit a set of CSNPs. So there are two methods to achieve the high availability, which is a checkpointing method, and the IETF TLV, which is a restart TLV, which is a TLV 211. So when we talk about the checkpointing method, is the ability to checkpoint the information to the standby RP. So the assumption here is that you have a standby. So in the sense, we are going to checkpoint some information to the standby. So when there is an event which occurs, then it has the ability to recover. And the IETF TLV method, which introduces the new TLV, TLV 211, that means it makes the neighbor routers too also to be aware rather than a standalone. So as you can see here for the checkpointing, it's actually, if the router itself, neighbor routers do not have to know whether they have the capability or not, versus with IETF TLV method, the neighbor routers also have to know. So on the checkpointing method, when the primary RP on the restarting router will checkpoint or save the neighbor adjacency information, and also it will checkpoint the database information. So the two things that are actually get checkpointed from the primary RP to the standby. I wish I could have made some animations, but sorry guys. But this slide is basically 2 points in the sense you want to checkpoint the neighbor and then the database to the standby or a secondary, or there are different names to the standby. So in case of a failure on the primary RP during the switchover, the secondary RP obviously has all the necessary information. That means the standby, in whatever the mode it is running, it has the information about the neighbors and also has the database. So obviously any missing information is going to get it from its neighbors. So this is the simplified version of a checkpointing method. And here are some of the optimizations that you can have if any of the interfaces that does not come up with the allocated interface time, wait time, that the routes that are learned from the neighbor routers are not considered in the routing table. So in essence, the checkpointing method involves the restarting event localized, means no other router in the network knows about it. But again, there is a timer. In the previous slide I was mentioning, if you do not come in a particular time interval, then I'm going to declare as a normal restart event. And it does not involve the restart capability on the neighbor routers. A similar mechanism actually also proposed in IETF, which is similar to checkpointing, where you checkpoint the information to the standby. In IETF, they actually, instead of checkpointing the information, they have introduced a new TLV, which is TLV 211. So the presence of this TLV indicates, when you send out a TLV, it indicates that the sender supports the new restart capability, and it carries the flags that are used to convey the information during the restart. That means neighbor routers need to understand that, this new capability. The format of the TLV 211, as we see there, it's a reserved, and then we have a SA bit set, SA, which is suppress adjacency, and then RA bit, and then RR, and the remaining holding time, and restart neighbor system ID. So in this case of the TLV 211 method, which is IETF, the restarting router sends this TLV 211 to the neighbors. And when it is restarting, it actually sets a bit, which is in this, the RR bit, which is a restart request bit by the restarting router. So that's my first bullet. Or in this case, actually the second bullet. The restarting router transmits its hellos with RR bit set. That means if the neighbor is aware, understands the TLV 211, what it is going to do, oh, my neighbor is telling me not to flap the adjacency. So in response to the TLV 211 with RR bit set by the restarting router, the neighbor router acknowledges back by clearing the RR bit and sets the RA acknowledgement bit. So the IIH with RR and IIH with RA bits. By this, we actually having, eliminating the adjacency flapping. And then the second event that we need to take care is the database synchronization. And then the neighbor router then sets the flags, since it realizes that there is a restarting router which is restarting, then it's going to set its SRM flags, and also it's going to send its CSNPs that it has, which is a complete sequence number of packets, which is basically like, here is my abbreviations of my LSPs that I have it in the database. Because in this case, the restarting router restarted does not have any information because it did not checkpoint anything. So in response to that, so the neighbor router sends its set of CSNPs, and in the meantime, all the other routers too also will keep sending to the restarting router. So eventually the restarting router will have all the information. During that time, the restarting router continues to set its RR bit set, means do not flap my adjacency. So there is a timer. So once it builds and, with the normal process and it has all the database information, then it's going to clear the bit, and that means, it has actually synchronized. So when the restarting router and the neighbor router have resynchronized their databases, the restarting router will run SPF, and after running the SPF, the local routing table is updated. And here is one which does not understand the TLV211. Then what happens? The neighbor, actually the restarting router, sends the TLV211, and the neighbor router receives it, does not understand it, so it does not set whatever the bit in it in this TLV211. The GORI details are the RA bit. So that means the restarting router receives a TLV or the IH packet, which is basically the hello packet, without the TLV211. That means it tells the restarting router, oh, my neighbor does not understand. So at that moment, this mechanism called NSF will be aborted. Suppress adjacency advertisement, which is the one other bit in the TLV211. This is not necessarily specific to the high availability, but the existing implementations can take advantage by having this bit set in the TLV211. So the purpose of this bit in the TLV211 is to avoid temporary black holes caused by the presence of the stale LSPs from the previous incarnation. That means if a router which is restarted, so if its LSPs are still lingering around in the network, so that means in this case, if I'm coming back again, in the sense if it came back, then I'm going to set the SA bit to tell my neighbors something, which is basically do not advertise my adjacency. So on the neighbor router, the adjacency to the starting router in the LSPs must be suppressed if IIH packet that is received has the SA bit set. This is figuratively speaking. When the SA bit is set, the neighbor LSPs have the IS neighbor advertisement to the other neighbors, but the neighbor router does not advertise the up, which is the adjacency which is up, in its LSPs. The two other fields in the TLV211, the restarting neighbor system ID and the remaining time. The remaining time, which is the holding time, which is in seconds. Again, this would have been good with some PowerPoint magic, but here is the sequence of steps that are actually happening if it is a starting router. So as I said, a starting router is a router which did not experience the restarting, but it is just a starting router. So it sets the so-called SA bit, which is equal to 1, which is the first arrow going from the starting router to the neighbor. Then the neighbor router receives, and the existing adjacency will be initialized. And in response to the SA bit, which is equal to 1, the neighbor router sends a hello and it suppresses the adjacency. And as long as the starting router is busy, it continues to set the SA bit. Then when it is ready to restart, or in the sense ready to come out of it, then it is going to set the RR bit. And in response to the RR bit, the neighbor router will set the RA bit, which is equal to 1. And then it will flood the set of CSNPs, which has all the database. And subsequently, when the starting router is clear, it clears the SA bit. And the adjacency will be advertised to the neighbors. As I said, this is not specific to the high availability, the setting of the SA bit, but it is a normal implementation can also take advantage of it. And this is proposed in the IETF draft. So these are the gory details. This is on the restarting router. So a restarting router to the neighbor router, when it restarts, as I was mentioning, it sets the RR, which is the restart request, to tell, hey, do not flap my adjacency to the neighbor routers. And in response to that, the NSF aware sets the RA bit and clears the RR bit. And the adjacency will be learned. Since the restarting router does not have any information, the neighbor router sets and floods the set of CSNPs, and in the meantime, from all other interfaces too, that the restarting router continues to receive. And the restarting router also, for the set of CSNPs, if it is missing or if it needs to act, it sends the PSNP. It clears the SRM flag, and that's the database synchronization. And this is without a neighbor router which does not understand the TLV211. So when you actually initially send the hello with the TLV211 with RR bit set, the neighbor router does not understand, so it sends a normal hello without the TLV211 that causes the restarting router to abort. And then as you see the last arrow at the bottom, the hello is without either of the RR bit or RA bit. And here is a slide which summarizes the differences between the two methods, the checkpointing method and the IETF method. In the checkpointing method, we checkpoint the adjacency and the neighbor information to the standby. So there is no mechanism of checkpointing to the standby, which is secondary RP or route processor. But with the IETF method, it has the TLV211 method. I mentioned the the checkpointing mechanism here I mentioned as incremental under the checkpointing, because the idea here is, you have a lot of information when you restart it, because it already has checkpointed the database, checkpointed the neighbor information. So any missing information is obviously incremental in the sense you are worried about the delta, the difference. Versus with IETF, the restarting router does not have anything. So it sends this TLV211 with RR bit set, so it's more of a bulk mechanism. And the checkpointing method, maybe the deployment may be much easier because it does not require neighbor routers to know the capability, because this is actually done on a router. So because you're actually checkpointing the information, versus the TLV-211, you need your neighbors to know or understand this new TLV-211. The second topic that actually summarizes the first one. The second one is the ISIs for IPv6. This has actually been there for a long time. But the following topic on multi-topology necessitates for me to put a couple of slides on IPv6. The existing ISIS implementations run IP, which is running for the IP. You know, they use the RFC 1195 and CLNS. Now we have this IPv6 routing capability that has been added to the existing ISIS protocol. When this is actually introduced for IPv6, so there are new TLVs that are actually added to the IPv6, and also a new identifier that actually has also been added to say that I'm IPv6 protocol identifier, to differentiate from the CLNS or IPv4. So the two new TLVs are the IPv6 reachability TLV, which is a TLV-236, and IPv6 interface address TLV, which is TLV-232. The TLV-236 is similar to the TLV-128, which has been around, what is it, for 15 years now, or TLV-135, maybe plus or minus 5 or 6 years or so, which is the traffic engineering extensions TLV. And TLV-232, similar to the TLV-132, which is the similar to kind of router IDs. The new IPv6 protocol identifier has the NLP ID value of 142. And for IPv4, it is a 204, and CLNS, it's 129. The main issue is if you are actually running with IPv4, with IPv6, you need to have a congruent topologies. The thing is, here on these slides, when I mention ISIS for IPv6, it assumes that it mandates if you want to run IPv6 along with IPv4, you cannot have incongruent topologies. It means the topologies have to be congruent. By no means I'm not an IPv6 expert, but more as an ISIS, at least to some extent. So the gory details of IPv6 addressing is not here, but the format of that TLV-236, which is and then TLV-232, the main point that I want to get away from this one too is that if you want to run IPv6, it requires a congruent. That means you have to have a same topology, both for IPv4 and IPv6. That means there is a single SPF done. But with the multi-topology, which is a new IETF draft, which allows the ISIs in a single domain to maintain a set of independent topologies. So I was alluding to that you can have a separate IPv4 or IPv6 topologies, and they do not have to be congruent. the current ISIS specification forces all the protocols carried by the ISIS to agree upon a common shortest path tree. And a single SPT means you need to have a congruent topologies, but it has its own problems. That means if you want to create some load balancing or any other mechanism between two independent address families, then you have a problem. For example, the last bullet says, it creates some undesirable effects. Unsupported network, which is IPv4 traffic, may be mistakenly routed via IPv6 only. An example, if you are looking from router A's perspective and if it needs to compute the shortest path to router E, assuming all the paths have equal cost paths, that is how the second picture on the right looks like, because that means a link between D and E is never used. Assuming this is simplistic topology, it's simplistic assumptions, but it explains the fundamental problem that it is there. That in a complex topology, changing the metric may be another issue that may attract some other side effect. So in essence, from router A's point of view, the link between D and E is never used. So the multi-topology gives the ability to distribute the traffic across all the links. In this case, I can have for IPv4 as similar to the previous slide, and for IPv6, I can have the C and E link not used, and I have IPv6 traffic go via the link between D and E. So each router knows which topologies. That means here we are saying for ISIS I'm running multiple topologies. That means, as an example, I just said IPv4 or IPv6. So each router knows which topologies it will establish adjacencies and build shortest path tree. And during the adjacency establishment, peers means the neighbors need to agree upon the topologies. That means between two routers on a point-to-point link, for example, they need to agree that if I'm running IPv4, the neighbor also has to run IPv4. I can't run on one side IPv4, on the other side IPv6. And these topology identifiers, that means the multi-topology draft introduces some new TLVs that I'm going to talk in subsequent slides. Introduces some new TLVs, and then there is a TLV that actually goes in this IIH packet, which is in this hello packet, which identifies to which topology that it belongs to. So the multi-topology membership advertisement is actually in the IIH packet, which is in the hello packet. And if you're running a normal IPv4 standard topology, which is a normal ISIS IPv4, then it has the identifier, empty ID of a 0. And the last one, it says the boundaries between the levels will be the same. That means if you have a L1, level 2, level 1 and level 2, that means that particular boundary is common across in any of independent of the multi-topology that it belongs to. So specifically speaking, for the advertisement on the LANs, so the LAN, you have DIS election. So that election process hasn't been changed with the introduction of this multi-topology support. And also, the routers on the LAN will always establish adjacency regardless whether they have a common empty set or not. in this case, when I mention about point-to-point, that they need to agree upon a common MT, they have to be in the same MT topology. But if it is a LAN, you don't have to. The reason is, again, it kind of goes back to that you have to have a consistent DIS. So the flooding is not changed, the DIS election process is not changed, and also the routers do not have to be on they do not have to agree upon the same MT. Versus on a point-to-point link, adjacency is formed only when the MT IDs are matching on at least one common MT set over the interface. And if MTID is not detected in the remote side IIH packet, that means if I send that I belong to so-and-so MTID, and if the neighbor sees that it is not in the part of the same MTID, which means it may not be running IPv6, then the local router won't include the neighbor in its MT LSPs, means I'm not going to form adjacency. The normal ISI's header has the overload bit, the attach bit, and the partition, the header itself of the ISI's. So the MT topology also has, when it sends the hello packet, it has the overload bit and the attached bit. So if I'm using a standard IPv4, then the normal ISI's header by default, which denotes if it is overloaded, the standard topology will set in the regular ISI's header. But if any other topology, then the overload bit and the attached bit will be set in the respective MT topology identifier. That's what I was mentioning, which is each MT topology, like IPv4 topology or IPv6 topology, has its own ATT bit, overload bit set in the MTTLV. And the two-way connectivity check within the SPF follow according to the MT to assure bidirectional reachability. The LSP flooding mechanism hasn't been changed. It's the same thing with if it is on the LAN, the DIS election, and the flooding on the LAN also hasn't been changed. So the new TLVs that this multi-topology draft introduces is TLV 229 and TLV 222 and TLV 235 and 237. So when you look at it, I've been stating, I'm trying to memorize it, but there are too many TLVs here. And we already talked about one TLV, which is TLV 211. But if you are, playing with ISIs, or if you have ISIs in your network, I'll make it a little bit easier because I think it just struck me the other day to memorize this, or at least remember to more than a day. The regular IPv4 129, which is actually denotes the protocol identifier that what it runs, like IPv4 or CLNS, or that's called TLV 129, which is the protocol identifier. So just increase it by 1 + 1, 2. So 229 multi-topology identifier. And you see the TLV 22, which is the traffic engineering extensions for the IS reachability, extended IS reachability TLV. So here, just slap a 2 in before, 222. Similarly, there is a 135, which is extended IP reachability TLV, 135, which is traffic engineering. So just slap a 1 + 1, 2, which is 235. So this is, in this case, for multi-topologies, IP reachability for IPv4. And I already talked about regular ISIs for IPv6, which is TLV 236. So this is +1, which is 237. If IPv6 is running for multi-topologies, which is TLV 237. The TLV229, which is the multi-topology identifier, is actually sent in the IIH packet to say which topology the router belongs to. Is that right? So here we have every topology has its own overload bit I was referring to, or its own attached bit. So we see the O and the A, and then there is a reserved bits, and then there is an empty ID, which is the ID of the topology identifier. Could be IPv4 or IPv6, and so on so. And basically, this has has 2 octets. The TLV222, which is similar to TLV22, the extended IS reachability, takes exactly the same format of TLV22, except the 2 octets on the top, it just has the additional 2 octets, which basically there are four of those bits are reserved, and it has the empty ID that it belongs to, like IPv4 or IPv6 and so on so. So if you actually break it down with the number of bytes in the bits, it has about 23 neighbors that you can include in the LSP or in this TLV. Similarly, 235, which is the 135 equivalent, extended IP reachability, same format as TLV 135, except on, that it has extra 2 additional octets on the top, the 4 bits reserved and the empty ID. This is IPv6 multi-topology, so it's different from TLV236, which is the normal IPv6 that we just talked. This is the TLV237. So the multi-topology draft does not make any recommendations or does not make any, basically does not make any recommendations or suggestions if you have, say, in your network TLV236 running, which is a normal IPv6 that we just talked, plus if you have a multi-topology, which is TLV237, which is also an IPv6. So the answer in this thing is, if you are running, either you run normal IPv6 with a normal topology where it has to be congruent, or if you go with a multi-topology, you can only do TLV237 and you cannot do 236. Basically cannot interoperate both of them together. The TLV229, which has this empty ID, the 12 bits we're talking about, these are the values that the multi-topology draft mentions, which is a standard topology, which is the IPv4 normal, which is 0, and then IPv4 in-band management purposes, TLV1, or IPv6, which is TLV2, and so on. So the standard topology, which is a 0, should only occur in the IIH packet, and it should not occur in the LSPs. So here, again, a simplistic example. I just took a pair of routers, some routers, what is it, 5 of them here. So EOR is the top router. So I'm trying to illustrate, if you are running IPv4 versus IPv6, can you have incongruent versus congruent? And here the assumption is all the equal cost paths. So if you have a congruent topology and if you are running multi-topology, obviously it will be the same, because there is nothing changed to necessitate between IPv4 versus IPv6, so they pick up the same topology, the shortest, from EOR. What says, if I change some metrics, then I can force the traffic to go where basically the link between the POO and the meaning is not being used, for IPv6. This is just an example to illustrate that you can share, the load across the links with multiple topologies. The MD5 authentication support, this is the other extension via the RFC, some number, I forgot, that it's proposed, and you may wonder why you need for ISI's MD5, as all of us know that, it runs directly on layer 2. But again, here is an extension if you want to have MD5. So the base specification of the ISO 10589 allows multiple authentication algorithms, and there is popular one which is a plain text, which is a 1. And they have introduced via the RFC 3567 a new MD5 type value, which is 54. The assumptions are the validation in support of MD5 is the plain text does not provide useful protection against intentional misbehavior. And obviously it's a plain text, so password is, it provides basically a weak protection against accidental errors or any misconfiguration. Here, that's what the disadvantages of having a plain text. So now what the RFC proposes is you have these 5 packet types, which is the regular LSP that you flood, and the LAN hello, and the point-to-point hello, and the CSNP, and then the PSNP, which is these 5 packet types, you can actually apply the authentication on any of these packet types, or on all of the packet types, or you can have on a subset of the packet types based upon what exactly. So there is a flexibility, on which, and even also it actually allows to which level you want to apply, whether you want to have it only for level 1 or level 2 only, or on all the levels. And if you have the authentication, then the passwords can be rolled over to without any disruption of the adjacency, flapping, or routing messages. Yeah, that's what I was mentioning. Like, if you want to have the control, you can have either for level 1 only, level 2 only, or on the LSPs only, or on a particular interface related PDUs like hellos or SNPs, or both, that you can apply MD5 authentication. And if you want to have additional security, error actually can be, configured to encrypt the string again, the password string. Unfortunately, I can't have any, user interface commands. The authentication TLV, which is a TLV 10, has the plain text, which has been there for a long time. So that the clear text password is, the type is 1, and the MD5 is the 54 that I was referring to. That's how actually it looks in the TLV. And the MD5 itself, the length and the value. So it's easy to identify if you do any of the show commands to see the difference between the plain text versus, a MD5 also by just looking at the length of that TLV. So from here onwards, the topics that I have here is more in terms of operator efficiency, to help the operator to improve, better performance of the protocol or better optimization in your network. Some of these came from the service providers or the operators that are running ISIs. So the default metric change. The default by the ISIs that it has on the links is 10. And if you are actually using, the traffic engineering extensions like the what is called a wide metric support, you can increase it to a greater value. But but this may not, with the narrow metric, which is a TLV, with the default metric of 10, if there is an accidental problem, then you may get into some issues. So I'm going to talk about on the subsequent slides, especially that the metric of 10 itself is not necessarily optimal with the interaction of the wide metrics, because with wide metrics you have a greater flexibility. So at present, operator may remove the metric from the interface or may not put it back. But again, here is the assumptions, because we have actually seen where people make human errors. So you have a metric, some XYZ, is it right? And you forgot to reapply because there is a maintenance window, something happened. And you restarted the router with new one. And then when the router comes up, it does not have any metric. What it is going to have? The default metric, 10. So if you have some applications that are running in your network, say for example MPLS traffic engineering, what's going to happen? All your LSPs going to get rerouted on this smaller cost path, because it just wiped out whatever it's been configured. So here we have a new router submode command, which is the metric which allows to configure and change the default metric. And this appears under the router ISIS, which you can actually apply for IPv4 or CLNS or any particular address family. The address family here refers to the one that we actually talked, the multi-topologies. And the passive interface metric hasn't been changed with this. So the passive interfaces always have a default metric value of a 0. The protocol shutdown is similar to, when you're bringing up a neighbor on a BGP peer, you can put neighbor shutdown and you can apply all the policies. Exact similar mechanism here too for ISIs. So you can say, router ISIs shut down and configure whatever you need to configure, or on the interfaces whatever you need to configure, and then you can enable it. Again, this introduces, obviously, you want to make sure that before you turn it on, that there are no any mistakes. It actually gives you a second-hand look before actually you turn the protocol. So you can do it either in the global mode or at the interface mode to remove the ISIs, in the existing, you have to do no router ISIs to remove it completely, which is no router ISIs, or in the interface mode you have to do no IP router ISIs if you are running for IP. So this one actually helps in the network operator if the network administrator wants to turn off the operation of the protocol without losing the protocol configuration. So when you have the no router ISIs, you actually have a CLI, which basically in this case is a shutdown when you have it on the interface mode. That no PDUs will be sent on the interface, and the received PDUs, which is basically a packet, protocol data unit, will be discarded. And if there is an existing adjacency, that it will be tear down, and we will not form any new adjacencies. On the router mode, we will disable the operation of the protocol, completely. That means, the LSP database will be cleared, and the ISIS routes in the RIB will be removed, and delete all the existing adjacencies. It's basically a granular. Whether you want to do it on the interface, you can shut down it, or if you want to do global mode, you just configure in the global mode. And here I'm just explaining, if you put it in the global mode, what happens? If you put it on the interface, what happens? If you put it on the interface, obviously you're not going to send any IIH packet. That means I'm not going to maintain any adjacencies. But if you put in the global mode, I'm going to clear the database, because global mode has to have the database. And also, if I have anything in the RIB pertaining to that, I'm just going to remove it, This is, again, one of those operator issues where you accidentally redistribute more number of routes into your IGP than what you can. So it's basically a band-aid that you want to prevent, so the router sucks up all the IGP routes. So to prevent the accidental redistribution of the routes into the IGP, here IGP could be ISIS or OSPF. Obviously we are talking for ISIS here, which causes, when you redistribute, if you do the accidental redistribution, obviously it's going to cause increase in the flooding, and also obviously it's going to result in severe network meltdown. And an example is like BGP getting redistributed, or BGP getting redistributed into another protocol, and in that another protocol in turn getting redistributed by ISIS. So think of the devil, and we have so many ways that we can, shoot ourselves. So the solution here is to address at the source. That means wherever you're doing the so-called redistribution, or at the L1, L2 router, the redistribution router, or at the source of the problem. So when you do the redistribution, you can still do it. So here is a method which actually controls how many routes that you can actually redistribute. So put a limit, 100 routes, 10,000 routes. Can you put 100,000 routes into ISIS? Okay, that's a question for you guys. You can. You have only 256 LSP fragments, and each LSP fragment can only put so many number of prefixes, and you can't even reach that, because that's why it's called IGP. It's not called BGP. So when you redistribute, the two conditions, right? The number of routes that you get redistributed, and you see the last bullet, which is the LSP full condition. That's what I'm actually denoting, which is the maximum number of routes. That means I exhausted all my LSP fragments. That means you gave me so much, I can only fit so much. I got each LSP with maximum 256, which is 0 to 255. So I reached my condition, which is called LSP full condition. I can't put any more. I don't have a 257. So that means all the routers are going to have, think of your database is getting huge, and every router has it, because, link state, you want to reliably flood the information, is it right? That means every router has this. So you have a command which is to control, which is the redistribute, maximum prefix, and you put a limit, and you put a threshold, and a warning, and a withdraw. So the limit is the high water mark, which is the upper limit. And the threshold is what is the threshold before I give you a warning message, which is 75%. And warning only, which means if I reach a certain threshold, it's just going to generate a warning. It does not control the limit. That means if I reach 100,000, say for example, I put a warning only, it's at say 80,000. It does not stop me to learn the additional routes. It just gives me a warning at 80,000, but I still continue to receive subsequent. So if you really want to put a hard stop, you want to put the withdraw option. And the limit itself, the first option applies only to the external IP prefixes when the limit is reached. That means it is external IP and it is not default routes or summary routes. So when you have a withdraw option, which is the last option, that means it's the maximum threshold, which forces to rebuild the LSP fragment again without the external prefixes. That means it's going to remove the external prefixes and then going to rebuild. That means I'm going to purge all the external prefixes that are there in the database. So here, as you see, this command doesn't have any default. That means you have to configure manually and what you want. So this itself applies to the redistribution. What you want to redistribute, how many routes you want to redistribute, what is the limit, what is the warning, and what's the withdraw option. But when you reach all the other routers, when it reaches the so-called the full condition, which is the 256 LSP fragments, they need to purge these the LSPs because they do not have they can't have in the database. So in this case, the LSP full has the option of suppress and external or interlevel and none, and by default it is the external option. That means external IP prefixes will be purged. That means if I'm having a hierarchy, level 1 and 2, and then say level 2, that means at the level 1 and 2 router, it does not suppress the interlevel routes. That means interlevel routes still go into the other domain, into the subdomain or into the domain. That means then in that case, you really need to have the interlevel option. So it is recommended that on the L1, L2 router to have additional option of removing the interlevel routes. As I was mentioning, by default, it is only external. So if you have a hierarchy in your network, level 1 and 2, and level 2 and so on, so then on the level 1 and level 2, you want to configure with the suppress level option. And this helps in several level 1 learn routes may aggregate on a level 1 and 2 router to cause the overflow. So this is the last topic on the agenda, which is the update on the IETF drafts. This by no means the exhaustive list of the updates, but here I try to summarize and obviously pertaining to what we have actually talked here. So I try to summarize where these drafts are actually and what's happening with them. We talked about the IETF method. The restart TLV method is actually approved by the IESG folks, and it's in the RFC, so it's going to become an informational RFC, which is the TLV 211. And about a couple of years back, the IETF working group came back and said, hey, we have all these vendors implemented ISIs. They're running good, but look at RFC 1195 or look at ISO 10589. Hey, there are a lot of caveats that what 1195 says no vendor followed, or 10589 says no vendor followed. So they actually about more than 2 years back or so, they formed what is called as a subgroup under the ISIS working group, and they try to do a job where to document some of the differences in terms of what is actually there in reality versus what is there in the draft. So they produced a document, and then later on it got split into two documents. So in either the case, it explains the caveats of the reality versus what is there in the document of 10589 or ISO 10589 versus the RFC 1195. So one of those documents is the draft, the ISIS IP interoperable. Oh, this actually has been approved by the, as an informational RFC. I think it is in the queue. So what does it has in it? There are so many things, as I just mentioning, what is there in the original draft versus what is implemented. For example, like TLV 131, which is there, and it mandates, like every implementer has to do it, which is IDRP, Inter-Domain Routing Protocol, whatever it means. Nobody uses it, nobody does it. So this document says, hey, no need to worry about this one. Similarly, TLV 133, we already talked about equivalent to TLV, computing for that, which is authentication TLV, which is the TLV 10. So then why I want to have again another authentication TLV, which is TLV 133? Nobody does implement, so just ignore it. So they document it, like that, which is basically unused features, which is TLV 131 or 1333, or usage of the overload bit. The 10589, when you look into, it has a different meaning of what is overloaded condition. But in reality, if you look at it, the way providers use the overload bit, it has a different meaning altogether, because they tie this with BGP. So the original reason versus what's the practicality. Again, it's got documented in this one. And there is no draft or no any paper talks about if you have a narrow matrix and then the wide matrix, how do you transition between narrow matrix and the wide matrix? So they documented that. And then there is ISH PDU. You know what it is? We talked about IIH. ISH is a hello packet sent by the router, which is the IS device, to see if there is end system. And you guys are here, you tell me how many end systems are there in reality, in the real world. There's all Windows, is that right? IP devices, not a DECnet, end system device that it understands that I need to send this special IIH packet. And it also says, the draft says that you need to send it on even on a point-to-point links. Guess what? Point-to-point links, you can't even have a end system, let alone on a LAN. So here is again it documents to say, hey, don't worry about if ISH packet. Send IIH to start off your adjacency initialization. Again, this is not a complete list, but I try to summarize some of the items in the draft that it mentions. And the second half of the draft, which is the same thing, so they're broken down into two things. One is for IP specific information and regular ISIS specific information. That was in the queue, and this got its RFC number before than the other one, which is RFC 3719. This is again covers the differences between the theory and the practice and tries to document or close the gap. So anybody who learning ISI, the first thing they hear is system ID, variable NSAP address. When you look at the 10589, the SysID, which is a system ID which uniquely identifies the system, is actually variable, which is between 0 to 8. But if you look at existing implementations, every implementation has a value of a 6. So that's the reality versus what's there in the theory. So that is variables which are constant. That's a variable in the 10589, but it is actually a constant in reality. And also the maximum area addresses. Think of how many areas you have in your network. Is it right? Like you have a net statement and a net statement and a net statement. You don't have that many. The default is it proposes 0 to 254, but you have only up to 3 maximum. And the constants which are variable. The other way around, it's not a variable, but it is a constant which are variable, which is a max age. So the 10589 says, your max age and the refresh interval have to be constants of, 1200 seconds and 900 seconds, which is 20 minutes and 9 minutes. But in reality, all the providers are who have implemented don't have that constant value. They have actually bumped it up. Like if you have like 400 devices, every other device sending a hello, so this actually has been bumped up, to a bigger value. So document the reality versus what is there in the theory. Similarly, the holding timer, it's the same thing. Padding of the hello PDUs. By default, everybody, we know like the difference between OSPF and ISIS. The ISIS, pads, to the fullest MTU. Like if you look at the hello packet, which is itself is a small packet, but you pad it to the fullest MTU. That's perfectly okay if it is Ethernet or smaller MTUs. But if you have a larger interfaces with newer interfaces that are coming in with a gigabit Ethernet or a POS or whatnot, which have more than 4K, it is good enough to send a hello, to realize and establish the adjacency. And the subsequent hellos, you don't have to pad it to the fullest MTU. Think of the devil if you have authentication again on top of it. So, that means authentication, that means your LSP gets larger, you have to do the SPF. So here it says you don't have to pad every packet as long as you establish the adjacency. Subsequent packets, you don't have to pad it to the fullest MTU. And the other things are zero checksum and the purging of the LSPs. That pretty much concludes my presentation. And there is some special thanks to the folks who actually have reviewed and helped me to actually specifically the Restart TLV. Les Ginberg is the co-author of the draft, and Mike Shan. So I bugged them so many times, and just to understand the RA bit, RR bit, where it goes, which direction, what is there, what is CSNP, and to Rena and Steven actually, who also helped me in reviewing and helping me understand better. Not the best, but still better. I still go to them. And the topics that we have covered, I have provided some URLs for the Restart TLV. It's going to become an RFC real soon, so this may get outdated, this URL. But it's in the IESG waiting group for almost like 3 or 4 months to become an RFC. And then ISIS for IPv6, the multi-topologies, and MD5 authentication. We talked about the recommendations for interoperable networks using ISIS and using IP ISIS. And the overload bit we talked about, not necessarily, but in terms of the caveats, so I highlighted that to see, because it has a good case study to explain what actually happens, if you don't, what's the purpose of overload bit in terms of BGP. That concludes my presentation. Any questions? Yeah, can you please come to the mic? So, yeah, please.
Bruce Hanna from Park. I'm trying to understand the with the high availability stuff you mentioned, especially with the IETF version. It looks like the router, which is either rebooting or deciding it's going down, needs to actually set some bits in its hellos that says, "Hello, I'm about to restart now." Is that did I understand that correctly?
That is true.
Okay, so in at least 50% of the cases where I've seen a router goes down and comes back up, it's not a clean shutdown. It's because a power supply is failing or the router is crashing. It's not a situation where the router can decide, oh, I'd better change my hello packets now before I crash and restart. Does this protocol even help with a hard crash situation like that?
It should help.
How can it when the router is not in a situation where it can even set bits in its outgoing hellos? It just, we're sliding in, a tech is sliding in a new board, right? And we get a parity error and the whole thing crashes and restarts.
Not necessarily in terms of that complicated, but the mechanism is both in the control plane and also in the forwarding plane. So it actually has a timer to send the what you call the fast hellos. So it should, and the draft actually talks about it in detail to send, if in case of emergency, what you should do. So it's not a normal hello that I'm going to send, like at so and so time. So when it is experiencing the restart, there is in the background, there is a mechanism already running all the time. So it triggers that mechanism to send the hello.
So it's sort of an emergency hello.
There is an emergency hello, yeah. And in fact, in the distributed architecture, nowadays you have the ability to not only at the control plane, but also on the forwarding plane to send the hellos to, so.
Okay, thanks.
Yeah. Any more questions?
Actually, a comment, I guess, on the previous, you wouldn't really want your router to keep forwarding when it's going down like that, parity error or hardware supply loss. You just want it to fail, at least I would, but that's just me. The tests, I guess, for authentication with the MD5 editions, has there been any interactions, been testing between the impact on like sub-second convergence? I wouldn't imagine it would be significant, but I just wondered if there'd been any actual, tests.
Not to my knowledge. This is independent processes, is it right? So I don't think it should conflict.
Yeah, it should only add, 10 or no more than 20 milliseconds.
Yeah. Not to my knowledge, yeah.
Hi, I have two questions about the high availability. First, on the IATF, it sounds like the SA bit, like to really dumb this down, the SA bit's kind of like an overload bit for just an interface. Would that be correct, or?
In a way, yes. Mm-hmm.
And then for the checkpointing, is there a provision in there where the two RPs are constantly syncing, or is that only on a crash on the primary, it dumps the secondary, or is that vendor specific, or?
I think I don't want to say vendor specific, but it's also implementation specific too, is it right? Whether you want to do periodic or you want to do, at one time, or, or maybe when you come up initially, is it right? When you establish. So I would leave as implementation specific, but at the end of the day, when it restarts for some reason, it should have the necessary information for the standby to do its job.
So is it sort of similar to the question that the first person asked, where there's something in the background all the time, so that if it does crash, it's getting ready to dump?
It's with the checkpointing you're asking? Because
Right.
with the checkpointing, it already has the information. It has already checkpointed. It's not necessarily that it does not have any, whether you want to do periodically, or or you want to do one time, or you want to do incremental. But obviously there is a missing information, then the normal update process will take care of it. Any more questions? Thanks, guys.